Welcome to Chapter 4 as we look at functions. A good part about functions is we use graphs and tables to represent the information. So let's start off here, using graphs to relate two quantities. The graph below relates the height of the water to the volume of the water in each container. Which graph goes with which container? Justify your reasoning. So as we interact with this material here, as you've noticed in the solve it, the change in the height of the water as the volume increases is related to the shape of the container. So we're going to take a look at how the graph changes based upon how the container looks. So in this particular graph, we're seeing where as the volume increases, the height increases, and then it changes. So it's going up and then it flattens out a little bit. So there's something here going on with that one. This one looks like, the second one looks like it's consistently being filled, but the height is not as high. And this one right here is consistently being filled, but the height is very high. So one that can, and we can kind of see where each one fits. Consistently filled, and the height is very high. Consistently being filled, and the height is low. And this one right here, my first graph, looks like that it is being filled, but as I get to the top, it changes. The height, more liquid is going in, but the height is changing. It isn't increasing as much. So graphs can tell us a lot about the relationship that's happening before us. So we got to pay attention to that. Our essential understanding is you can use graphs to visually represent the relationship between two variables and the quantities as they both change. So consider the two variables as we look at these things. Let's analyze a graph. This graph shows the volume of air in a balloon as you blow it up until it pops. What are the variables? Describe how the variables are related at various points on the graph. Maybe you want to pause and consider these two before I continue talking. So the two variables that are played out here are, we can see here, one of them is the volume of the air, and the other one is the time it's taking to do these, to fill the balloon. The variables are the volume and time. So kind of explain as we look at the graph happening here. If the graph is playing out, it goes up and it plateaus right here. It's plateauing because this is the point when I need to stop and take a breath. So I'm filling it up, and I take a breath, and I fill it up again, and then I take a breath, and then blow, and then take a breath, and then I scare myself. But then completely the air comes out of the balloon, and there's no volume of air in the balloon as time has passed. Your turn to try it. What are the variables in each of these graphs? Describe how the variables are related to the various points on the graph. For instance, I want to know kind of what's happening here when it's plateauing, and then what's happening here. The same here, what's causing this, what's causing this, and maybe why here, maybe why this one's longer. Consider why these are changing, why is it consistent or is it changing? So press pause and let me know what you came up with. Looks like what's happening in the first situation, my two variables are length and its time, and as time passes, the length looks like it is decreasing. So in this particular situation, pieces are being cut off. Thus, the length of the board is shrinking as time goes on. In this particular situation here, must be when it falls off, and then this particular time must be when the cutting is happening. The cutting is happening, and then it falls off. And then it's happening, and then it falls off. And it looks like they got tired of cutting at this point. And we've got B, we've got June's phone cell plan. We have the minutes of calls happening and the cost changing. And we've got a plateau going on here. Looks like the cost is staying the same all the way through, and then it changes. So maybe this is like a rate plan or something where your first amount of minutes is prepaid and the cost does not change. And then at some point in the situation here, right here is when you get charged for more, maybe for more minutes. Tables and graphs can both show relationships between variables. Data from a table are often displayed using a graph to visually represent that relationship. A band allowed fans to download its new video from its website. The table shows the total number of downloads after 1, 2, 3, and 4 days. Which graph could represent the data shown in the table? You're welcome to press pause, try your answer, and then play and see how this plays out. I'm going to keep going though. So I'm looking at A, and when I see A, I see a nice consistent linear relationship as it's growing consistently, but when I look at the data here, it's definitely not changing consistently. It is increasing, which graph A shows, an increase as the day continues, but this does not match my graph. I'm going to look at graph number 2. There's something interesting happening here is the downloads have increased, but then it does slow down on the graphing. So when I look at my data, I'm looking down and I'm seeing that the information does not slow down, and in fact it increases more. I'm going to look at my graph D, which is indicating that as the day continues on, my number of downloads, or as the number of days increase, the number of downloads decrease. This would happen more for like this particular site because less people need to see it because it's passed on. This unit has passed on, so less people are watching this. But for this particular situation, as the days increase, more downloads are happening. So it's not D, it is indeed B. As the days increase, so do the number of downloads. The two variables that are playing out here, we can see is the days and the total downloads. Why don't you give it a try? This table shows the amount of sunscreen left in the can based on the number of times the sunscreen has been used. I've never bought sunscreen from a can, but in this situation, apparently you can. So which graph could represent the data shown in the table? Press pause, give it a try. So it looks like this one is I'm seeing as the days, or as the number of uses increases, the amount being used is going down very slightly. The amount of sunscreen is going down really slow. So I'm looking for something that's a slow change. This one's a linear relationship. It's going down. In fact, it goes down to 0 right here. I still have sunscreen in the bottle after the 3rd use, so it can't be this one because that's saying there's none left. This one indicates that it is going down and then a lot more is being used. This looks pretty consistent as it travels along here. This guy shows a nice consistent, just a little bit taken out each time. It's still linear, kind of happening at a good same amount. So it's going to be C. In problem 2, the number of downloads, which is on the vertical axis of each graph, depends on the day. Okay, depends on the day that's happening, which is on the horizontal axis. When one quantity depends on the other, show the independent quantity on the horizontal axis and the dependent quantity on the vertical axis. So this is basically indicating to us is that on my horizontal axis or my x-axis, you're going to see the independent quantity. That is the information that is just going to move along independent of what is happening with the other variable. Like for instance, time. Time is a very common element to have on my x-axis because it is going to continue on and move along no matter what's going on over here on my y-axis. If it's amount of money or if it's temperature or no matter what's happening on my y-axis, time will continue on. That's why it tends to be an independent variable. My dependent variable, though, really depends on what's happening on my x. So if somebody says, what's the temperature? We say, well, it depends on what time you're talking about. If somebody says, well, what's the cost for the number of puppies? Well, it depends on how many puppies you buy. So maybe on this one, my dependent variable would be dependent on how many puppies I buy, which is my independent variable. So you kind of got to talk through a little bit which one is independent and which was dependent. So let's try this out. A model rocket rises quickly, then slows to a stop and burns its fuel out. It begins to fall quickly until the parachute opens, after which it falls slowly back to Earth. What sketch of a graph could represent the height of the rocket during this flight? And then look at the sections. You can go ahead and press pause, give it a try, and then see what I found. All right, here's the graph I came up with. My two variables would be, of course, as time is traveling along the independent variable, it is just moving no matter what the rocket is doing. Even if you don't fire the rocket, time is still moving along. And this is going to look at height. We can consider a lot of different variables, but this one's considering height. So the rocket rises quickly, then the rocket stops rising because the fuel burns out. It falls quickly. As it reaches its height, it starts falling quickly, and then the parachute opens, thus slowing the height dropping, and then it falls slowly until, of course, it hits the Earth. I guess my graphs, the rockets that I usually do, end up going about right here and stopping right there, because my rockets usually land in a tree. Why don't you give it a try? Press pause, read through this, draw your graph, and label some things. Let's see what you come up with. As you can see in this situation, this is not at 0 because I'm starting to swing, so I'm already off of the ground, the distance from the ground. But as I'm pumping and swinging more and swinging, I'm getting off the ground, I'm going down, I'm flying way up in the air, then I swing back, and this must be me slowing down in that situation until I come to a stop right here. And again, it doesn't go all the way down to 0 here because I'm still sitting on the swing and I am off of the ground just a little bit. But B says, if you jump from the swing instead of slowly swinging to a stop, how would the graph part be different? I mean, maybe this could play out up here when you get to your highest point and you jump off. So let's say you're pumping, you swing, and you're right here at the top in the forward motion and you jump off, you are going to drop very quickly, probably to the ground. Unless, of course, you're like my rocket and you land in a tree, which would be sad, but a really good story. All right, there we go. So keep practicing this stuff. We'll talk more about it. Now I'm going to go see if I can find a can of suntan lotion and spread it all over the neighbor's dog.